Welcome back. So here is a soda can. It's 355 milliliters, just a typical soda can that you can see. And it will be a perfect cylinder for our problem here. Let's get rid of this. And the soda can is 6.2 centimeters in diameter. The volume is 355 milliliters. And it has a mass of 20 grams. So let's see. Soda can looks like so. Okay. This is the length of the soda can from here to here. And this is R, radius of the soda can. And this is the volume of the soda can. So we're not given the length of the soda can. We're going to need it. So let's find it. So I know that the volume will be, it's a cylinder, so it's pi r squared times L. And so L will be the volume divided by pi r squared. The volume is 355 milliliters, so that's 0.355 liters. But the liter is 10 to the minus 3 cubic meters, so I'm going to multiply by 10 to the minus 3. So this is now in cubic meters. Divided by pi, the diameter is 6.2 centimeters, so that's 3.1 centimeters for the radius, so 3.1, times 10 to the minus 2 to change it to meters, and then we need to square it. And let's see what the length is for this soda can. I need my calculator here. So I get, first, let's do the denominator. So 3.1 times 10 to the minus 2 squared, multiplied by pi. Okay, hopefully I do not make any mistakes. That looks good. And then invert it and multiply by here. Times 0.355 times 10 to the minus 3. And this gives me 0.1176. 0.1176 meters. That's 11.76 centimeters. It sounds reasonable. 10 centimeters is this much. It sounds reasonable to me. So I don't think we made a mistake. Okay. Sounds good. We haven't even read the problem yet, completely. The soda can, this empty soda can, it will have a mass of 20 grams. Okay? We're going to fill it to halfway. So it is halfway full of water, and it is floating upright in water. So you put water on it, or in it. Here's the soda can. I'll make it a little smaller now. You put water in it, so it has some water here. It has some water. And it is below water. Right? So it is filled with water. Maybe it's filled with water up to here, let's say. This is the water inside the soda can. And now it floats. It is floating. So they would like to know how high the length of the can that is above the water level. Let's call this D here. And this whole thing is L. This whole thing is L. So this is L. So what's below the water level, I almost said sea level, will be L minus D. And this will be related to the water displaced. So what are the forces on this soda can? Why does it float? Well, there is gravity pulling it down and the buoyant force downward. There is gravity, mg, and then there is the buoyant force. Okay. First, let's calculate the mass times gravity. mg, the mg part, it will be, the mass consists of the mass of the soda can plus the the mass of the water inside it. The mass of the soda can is 20 grams or 0.02 kilograms plus, and then at the end I have to multiply by G, plus the mass of the water inside it. The mass of the water inside it, well, it's half full, so the water inside it is half of this. Okay? Half of this. So let me do this. So 355 355 milliliters divided by 2, that's 177.5 grams, and 177.5 milliliters, and water is a gram per milliliter. So it is 177.5 grams. If you divide by 1,000, you will get 0.177 kilograms. So it's 0.1775 kilograms of water inside it because it's halfway full. This is the mass of the empty soda can, and that's that. And then times G, which is 9.8. So let's find the mg parts. So we get mg, that's the force of gravity on the can plus the water inside it. So over 1,000 on this, and then plus 0.02, and then times 9.8, and we get 1.9355 newtons. All right, that's the mg part. Now, the buoyant force. The buoyant force will equal to, it's the weight of the fluid that has been displaced. So what's in the fluid? It's inside water. So it will be the density of the water times the volume of the water it displaces times gravity. So I'll put density times gravity first, and then the volume of the water that it will displace. The volume of the water it will displace as much as equal to the amount of the volume of the can that's submerged. The volume of the can that's submerged is the L minus D, the height, times the area. So it will be L minus D, right? Imagine you have a cylinder, here just only this part of the cylinder, the L minus D times the area. So it will be L minus D times the cross-sectional area, which is the pi r squared. Pi r squared. All right, pi r squared. And and so we get the following. We get the net force has to equal to 0 because the can is floating. So we get the buoyant force because it's upward minus mg should equal to 0, and therefore the buoyant force equals to mg. So that means rho g pi r squared L minus d will equal to mg. The mass times gravity. And mg is the 1.9355. Okay. So L minus D will equal to 1.9355 divided by rho g pi r squared. Rho is the density of water, that's 1,000. G is 9.8 as usual. And then pi is pi, 3.14. And then r squared. What's the radius? Again, we said it's 6.2 centimeters in diameter, therefore it's 3.1 centimeters in radius, so that's 3.1 times 10 to the minus 2 to convert it to meters, and then we have to square it. Okay, we need to get this number here. So let's do that. So divide by 1,000. Divide by 9.8. Divide by pi, 3.14159. Okay, that's how many digits I know of pi. And then divide by 3.1 squared. And then I get 0.0654. Okay. Therefore, D equal to L minus 0.0654, and L is 0.1176 minus 0.0654, and we get 0.0522 meters. That's the volume that is above the water. And that volume above the level that's above the water is approximately half of the can, approximately half of L, which makes sense because the can is basically water here, only 20 grams of the can when it's empty, and so it has not, so it kind of only halfway, barely more than halfway below. I think got it as what? About 44% is above, and therefore what? 56% is below. Okay, so one more problem. All right, let's get to it. This problem will involve some calculus. So imagine you have a tank here. It's like a box. It's filled with water. Right? It's filled with water. And I would like to know how much force is on this right wall. And the force will be, first of all, the pressure, there will be force on it from the atmospheric pressure plus the force from the water pressure this way. And the force from the atmospheric pressure here, remember the pressure when it, I just want to know just the net force on it from the pressure. So as you go deeper, outside it's atmospheric pressure, so inside it would be the atmospheric pressure plus the depth, and then from the outside there is the atmospheric pressure, so I will just ignore the atmospheric pressure because there is atmospheric plus the water pressure from the inside, and then the atmospheric from the outside, so they simply cancel the atmospheric. So I just have the pressure from the water itself. And the pressure from the water is, so ignore the atmospheric pressure, in other words. So you have the pressure, just the pressure of the water would be the density times gravity times the depth, right? And the depth will be, let's say if you go deeper, I'm taking this to be the zero, so so the depth here will be, think about it, what would it be? It will be 1. All right, so as I go deeper here, let's say if I'm here, if the height here is y, and this is h, so this is, if I'm here, right, if I'm all the way here, that's y, and this is h, so this portion here will be h minus y. So the pressure will be rho g. As I get deeper, you'll get the h minus y, and then plus the atmospheric pressure. But I'm ignoring that because there is atmospheric pressure from outside and atmospheric pressure from the inside. So that's the pressure as you go deeper. Now, how much force is there? The force, let me call it dF. How much force is there on this slice? Let me take a slice here of thickness dy, right? Thickness dy, and the width is y. So dF will be the pressure times the area, which is dA. And the area is the width times the dy. Is the width, W, times dy. So to find the total force, so the total force will equal the integral from y equal to 0 to y equal to h of the pressure times W times dy. So I put the W outside, that's the constant. The pressure is rho g h minus y, rho g times h minus y, and then dy. All right? And so we get rho g W, rho g times W, and then times what? The integral of h will be hy, h dy will be hy, and then evaluated at h, that gives me, so let me put it this way, hy, and then minus, the integral of y will be 1/2 of y squared, evaluated between 0 and h. 0 and h. And, well, we get what? We get rho g w, and then h times h will give me h squared minus 1/2 of h squared. So that's half of h squared. So we get 1/2 rho g w h squared. And I think I'm happy with this because the pressure varies linearly, so the average is as if the force, it's like you use the average pressure in the middle there. Yeah, I think I'm happy with that, with the solution there. So in the book they say if you have if you had a spring that's holding the walls, so here is, for example, if it's empty and you have a spring, the spring would not be stretched nor compressed. So now if you want to put water in there, you don't want the water, you just want the walls to be held by the spring. So what you do is you pre-stretch or pre-compress the spring. So you basically pre-stretch the spring, and then basically put a stretch spring on the walls so that the spring will be pulling on the walls, so that when you put the water in, eventually you will have the force from the water, the average force from the water will equal to the force of by how much you have pre-stretched the spring. And so it ends up being this. And then the second part of the problem, which I asked you to not worry about it, they say, where would you put the spring? You would put it at some point, because the reason you would put it at some point, maybe the middle, maybe not, and where, sure, the force cancels, but there could be a torque that will either open the wall this way or open it this way. It turns out to be kind of a really long expression, and so I decided to just, I don't think there was much learning in it, so I decided to, I think, ignore it. And I think this should conclude our chapter 14, I think. There is a question in the book, I think it's at the end of the chapter, and I just want to sketch it for you. It has to do with draining a cone. Say you have a cone that looks like this. Let me draw the x-axis here, and the y-axis. And the cone looks like this. That's the cone. It has radius, let me call this r, or r0. And the height here is h0. Okay? And it's filled with water. This thing is filled with water, filled to h here. And what you do is you dig a hole here, and the hole has radius r. The hole has radius r. So the diameter would be 2r. And so the water will start flowing this way. Let's call here V1. This is V2. And the pressure here is P2. The pressure here is P1. And the question is, how long will it take it to drain? How much time will it take it to drain, given these? And the water level here will start dropping, and V1 is much less than V2. And so let me just show you how to work with that. So first, this is the y-axis, and this is the x-axis. So we conclude that y will be what? It's what's the equation for this line? Y will be the slope times x. The slope is h0 over r0. h0 over r0 times x. That's the slope. And so another way you can say it is x will be r0 over h0 times y. Okay? So now, as the water drains, at some point it will be here. So this is x, and this will be y. So let's write Bernoulli's equation. Notice both of these are open to the atmosphere from here and here. So the pressure 1 and pressure 2 are both equal to atmospheric pressure. So I will write P1 plus 1/2 rho V1 squared plus rho y1 equals to P2 plus 1/2 rho V2 squared plus rho y1. This one is located at y equal to 0, so that's 0. P1 and P2 cancel, both are atmospheric pressure, so we end up with this. So we get the following. Let's move this to the other side, so I get rho y1 will equal to 1/2 rho V1 squared minus V2 squared minus V1 squared, like so. Move the V1 there. And V2 will be larger, much larger than V1. And so we will get rid of that also, multiply both sides by 2. So we get the following here. So we get, let me factor V2 out. Let me factor V2 out. So I get 2 rho y1 will equal to V2 squared times 1 minus V1 over V2, the whole thing squared, like so. The whole thing squared. I factored the V2 out. Now, V2 is much larger than V1. So, in particular, V1 over V2 would be much less than 1 because V2 is much larger. And then when you square it, it would be even much less. So we're going to, whenever you see V1 over V2 and it's squared, we're just going to ignore it because it's too little. For example, let's say V1 is equal to 1 and V2 is equal to, let's say, 10, right? Or 100. So V1 over V2 would be 1 over 100, which is 0.01. However, V1 over V2 to the power 2. So maybe we want to keep to this factor, but this is definitely, we can ignore here because it's 0.0001. So this we're going to throw away. We're going to say this is approximately 0. So, and we're going to ignore it because first, the solution would be fairly close. Secondly, the integral would be very tough if we keep this the same way it is. So now we get, let me put it this way, 2 rho y1 equals to approximately V2 squared. V2 squared. And now I'm going to get what V2 is in terms of V1. The continuity equation says area 1 V1 will equals to area 2 V2, and area 1, the cross-sectional area here will be pi x squared. So you get pi x squared, and then V1 will equals to area 2. Area 2 is, there is an opening here of radius r, so there is pi r squared V2. So the pi goes away, and so you get V2 will be x squared over r squared times V1. And x is y, is r0 over h times y. So you get r0 squared over h 0 squared times 1 over r squared times V1. I hope I did not make a typo. I think I have it right. Yeah, x squared. Get this stuff. Oh, I forgot the y. Yes, here's the y. The y, and it is y squared. So now I'm going to, instead of V2, I'm going to replace it by V1. So I get this 2 rho y, not y, just y. The height is y. 2 rho, the height, yeah, the height is y, is equal to, or approximately equal to r0 squared over h0 squared, and then r squared. R is a constant, it's the radius of that wall, the hole in the middle. And then I have y squared v1. Oh, I'm sorry, we're squaring this. So this should say r to the fourth, h to the fourth, r0 to the fourth, y to the fourth, v1 to the second power. Everything should be squared. And on both sides I have a y, so let me cancel the y and then move everything to the other side. So I get the following. I will get v1 squared we'll multiply everything by, I feel like I'm missing a 2 or something. Maybe not. Let's see. So 2 rho, you cancel one of these, so this becomes cubed. So you get, and we're dividing by it, so it's y to the minus 3. And then we have h0 to the fourth power, r to the fourth power, divided by r0 to the fourth power. And I hope I have it right. Let's say h0 r to the fourth, 2 rho. Yeah, I think it sounds good. And this is v1. And I'm going to take the square root of both sides now to get just v. Yeah, it's not, you see, I canceled the row. I knew, yeah, this is G. This is G. It didn't look right at first. So G. So now, yeah, so this is G. Okay, now it's good. The density should cancel. And so take the square root of both sides. So I get V1 will be radical 2G. And then the square root of this stuff will be H0 squared R squared over R0 squared. And then the square root of this will be y to the negative 3/2 power. But what's V1? V1 is this way, and so V1 is negative dy dt, right? Y is shrinking, so V will be the negative of that. So this is negative dy dt. So this is negative dy dt. Negative dy dt. So I'm going to multiply both sides by y to the 3/2, so I get this. Negative y to the 3/2 dy dt equals to 2g h0 squared r squared over r0 squared. Let me make sure I have enough time. Yeah, I do. R0 squared. And multiply both sides by dt, so I have dt here. Now we will integrate. We'll integrate from y initial, which is h0, to y final, which is 0. So from h0 to 0. And this one we're going to integrate it from, all of these are constants, so we're going to integrate it from 0 to the time at which it drains. I'm going to call it capital T. And the integral of y to the 3/2 is just 2/3 y to the 1/2, or 2/3 y to the 5/2. And I'm going to switch the limits so it becomes positive. So when you switch the limits, you have this from 0 to h0. And so this integral here would be 2/5 y to the 5/2. Evaluated between 0 and h0, and h0 is equal to 2g square root h0 0 squared, r squared over r0 squared. The integral of dt is t evaluated between 0 and capital T is simply capital T. And so now we can solve for t and get it. So the time it takes to drain it is capital T equal to. This evaluated between 0 and h0 would be h0 to the 5 halves. So it would be 2/5. And h0 to the 5 halves, when you divide by h0 to squared here, it just becomes h0 to the 1/2. h0 to the 1/2. And we're going to multiply by r0 squared. And we're going to divide by this. I'm solving for capital T. So we're going to divide by r squared and 2g square root. And h0 to the 1/2 is the square root of h0, so capital T will be 2/5 h0 over 2g, all of them under the same square root. And here I have r0 squared over r squared. Hopefully I have this correct. And it looks correct. All right, I will stop here.